A value of actual fin effectiveness for the shown fin array was found experimentally. An analysis was attempted using the general case of the Ellenbos correlation that underpredicted the heat transfer by about half. The analysis was repeated using the fully developed constraints of the Ellenbos correlation, and results more accurately predicted the heat transfer of the fin array. The fin array was to be tested on a Darlington transistor. Since the base of the fin array fits nicely on the heated collector tab of the transistor, and power dissipated through a transistor is easily controlled by adjusting the transistor's base voltage. Since the transistor needed a resistive load, a testing apparatus was created to draw current through the transistor. The selected resistive load was 3 12-volt halogen bulbs. They were directed away from the transistor, and aluminum foil surrounded the bulbs to avoid any possibility that the bulbs might radiate and heat the transistor or fin array. The bulbs were superior to a traditional circuitry type resistor, since the bulbs are designed to dissipate more heat without being damaged. They also did not cause any damaging voltage spikes like an inductive load such as a motor would cause. Voltage was supplied by a 12-volt battery that was maintained above 12.4 volts at all times throughout the experiment. Since PWM signal forms a linear relationship with duty cycle, applied voltage could be found using interpolation of the PWM settings. Current through the transistor was found using an ammeter. Knowledge of the current flow through the transistor and voltage across the transistor could be used to find power dissipated by the transistor. Current and voltage had to be found in each junction of the transistor to find total power dissipated. Controlling power dissipated through a bipolar junction transistor, such as the one being used, requires control of voltage applied at the base of the transistor. The base voltage was adjusted on an average basis using a pulse width modulation, or PWM signal, generated by an Arduino microcontroller. The duty cycle of the signal is adjusted in discrete settings from 0 to 255. As seen in the figure, a maximum operating temperature of 150 degrees Celsius, which is the manufacturer's parameter, lies between PWM settings of 16 and 17. We can see how settings 15, 16, and 17 form a nearly linear relationship between power and temperature, so linear interpolation is justified in this case. Performing a heat transfer analysis of the fin array using the general case of the Ellenbos correlation and treating the fin array as thin vertical channels, the correlation assumes heat transfer in the developing region of the velocity profile. However, this is almost half the actual fin heat transfer. Calculations for array efficiency were performed treating the fins as an array of rectangular fins. There is another case of the Ellenbos correlation that applies when there is a constraint of a long channel. That is the correlation for the fully developed region. Whereas before it was assumed that each row of rectangular fins was short enough that the velocity profile for each fin was in the developing region, the results show that instead, assuming that the velocity profile is fully developed is a more accurate assumption in this case. A mention of a geometric relationship for the Ellenbos correlation is made in the book Fundamentals of Heat and Mass Transfer 6th edition by Frank and Cropera. The book states that the fully developed case of the correlation applies if a length ratio is met. The S divided by L number is the ratio of the gap of the flow channel to the length of the flow channel in the flow direction. The textbook does not state values for this ratio when the fully developed assumption is applicable. Instead, it just states that this case applies when the ratio approaches 0. The S divided by L ratio in this case is 0.64, which must be close enough to 0 for this to be the case for the correlation. The fin array analysis underpredicts the heat transfer of the transistor by about 13%. This is primarily due to the assumption that all power dissipated in the transistor will transfer through the fin array alone. This is a good assumption, but it isn't perfect. Heat will also transfer through the case of the transistor, the pins, and the rest of the collector tab not covered by the fin array. By neglecting heat transfer through other means than the fin array, we expect the actual heat transfer to be a little higher than the analytical heat transfer, which it is. In conclusion, the Ehlenbach correlation for long channels applies when under the assumption that the velocity profile is fully developed. This is probably due to the low fluid speeds that we would expect from free convection of air. It is also worth noting that in this case the rectangular pin fins are quite long and roughly resemble the shape of a channel. For a rectangular fin array of this type, I would recommend using the Ehlenbach correlation if using free convective heat transfer. Additionally, I specifically recommend using the correlation for the fully developed region if the ratio of gap between fins to the length in the flow direction is smaller than 0.64.